My slides up. Oh, cool. Okay, so let's jump right into it. So today there's going to be, I counted 5 talks on the schedule about sharding protocols, and there's been a lot of research on how to shard consensus and how to shard execution of the blockchain. But I think what's equally important is how do you actually shard the verification of the blockchain, because it's all well and good that we can have consensus that can reach consensus on transactions in parallel, but we also need to make it possible for people to independently verify that blockchain, or participants within shards to independently verify the blockchain or have some guarantee that the blockchain is correct without having to actually download all the data in all the shards, because that would defeat the point in sharding. So effectively what we have here is this kind of trade-off. When you're trying to scale a blockchain through on-chain scaling, there's this kind of trade-off between decentralization and security. Because in theory, the more on-chain throughput you have, the less decentralized the blockchain is, because there's more data that you have to download in order to run a full node to verify the entire blockchain. So as a result, people would have to run instead what's called light clients. And light clients are basically nodes that only download block headers, and they simply assume that all of the transactions in the blocks are valid, and they simply trust that the majority of the consensus participants are being honest. And so they make this honest majority assumption when it comes to assuming that blocks contain valid transactions. And that's very different to how full nodes operate, or how you would operate if you're checking the entire chain yourself. Because if you're running a full node, then you only rely on this majority assumption to prevent double spending attacks. But with light clients, you rely on this honest majority assumption to prevent miners from doing things like generating money out of thin air or stealing people's money, because they can effectively include invalid transactions in the blocks. So a big question that we might want to ask ourselves is, how can we actually make it possible for light clients or non-fully validating nodes to reject invalid blocks, so that they don't have to trust the miners and they don't have to assume that the majority of the consensus set is honest? And this is a very important question to sharding, because when you're running a sharding protocol, effectively the most natural way to do it is, if you're a consensus node in a particular shard, you would need to run a light client for every other shard to be able to do cross-shard transactions and to know what the state of every other shard is. But you don't actually verify the state of the shard. You just assume that all of the shards aren't corrupt. So it's very important to actually try to eliminate that assumption, because if you have 100 shards and one of them is corrupt, then that could poison all of the other shards. So we could basically use what I'm going to be presenting today, fraud proofs and data availability proofs, to kind of eliminate this honest majority assumption, to allow light clients to have some assurances that blocks contain only valid transactions without actually having to download the entire blocks themselves. So this is what I'm going to be presenting today is based on a paper which is a joint work with Alberto from UCL and Vitalik from Ethereum Research. The code is there's also code, and the paper is on the presentation if you're interested to have a read of it. So the basic idea of fraud proofs, it's actually a very old idea. So the idea of fraud proofs is that you have light clients and you have full nodes. And full nodes download all of the blocks, as I mentioned. They download all of the data in all of the blocks, and they verify the data independently. But light clients only download the headers of the blocks. So they assume that they don't download the actual data in the blocks, and they simply assume it's correct. And sometimes they ask full nodes for Merkle proofs of transactions that are relevant to them in these blocks. And that's if you download the Android wallet on your phone, that's what would happen. It's basically running a light client that only downloads the headers and receives Merkle proofs of transactions that are relevant to the addresses that you own. The idea of fraud proofs is that if a full node downloads some transaction data and realizes that this data contains invalid transactions, then the full node can send the light client a succinct proof that this is the case. And the light client can reject that block header and move on to the next valid chain in the blockchain. So the original Bitcoin white paper actually mentions this idea called alert. It's mentioned as alerts. And alerts are basically messages that full nodes can send to light clients to alert them that some block is invalid. But this doesn't quite work very well because I can just launch a bunch of full nodes and send a bunch of messages to the same light client to tell them every block is invalid, and that would basically force the light client to download the entire blockchain, so that's basically a denial of service attack. So in the worst case scenario, this alert scheme, the efficiency of this alert scheme requires light clients to download the whole blockchain, which effectively is like running a full node. So it's not really that much better than running a full node in a worst case scenario. So there's also been some earlier work on compact fraud proofs, which is the idea that you could actually just have more compact fraud proofs for individual transactions rather than the entire blocks. But these early ideas of compact fraud proofs, they propose a different fraud proof for every single type of way to violate the protocol rules. So for example, you might have one type of fraud proof for a transaction that spends an invalid UTXO. You might have another type of fraud proof for a transaction that spends more money than it should, and you might have another fraud proof for a block where a miner has mined more reward than they're allowed to. But what we can do is we can actually improve on this and simplify the entire fraud proof system into one single fraud proof. So that makes it a lot easier to implement. So if you consider the blockchain is basically a state transition system, so you have some block X, and then you have block X plus 1, and then you have a bunch of transactions in block X plus 1, and if you apply all of these transactions sequentially, one by one, they change the state of the blockchain in some way. And you can imagine there's a state transition function that takes in the current state and a transaction and returns the new state or an error if the transaction does an invalid operation. So then what if one of these transitions is incorrect? Or what if one of these transactions are illegal? Then we basically need a compact way to prove this. So basically, there's this idea of committing to the state in the block header. So you can represent the entire state of the blockchain as a single Merkle root, and Ethereum and other blockchains already do this by using a structure called a Patricia tree. And the idea is that you can basically store the blockchain as a key value store. So with an account-based system like Ethereum, that's already the case. With a UTXO-based system like Bitcoin, then you would have to imagine that the keys would basically be the UTXO IDs, and the values would be 1 if the UTXO is unspent, and 0 if the UTXO is already spent or does not exist. So effectively, it's basically a Merkle root that represents the state of all the UTXOs that could ever exist in the system, and whether they're spent or not. So more recently, sparse Merkle trees have started gaining popularity, and Ethereum 2.0 is actually it's called Serenity now. Serenity is planning to actually use sparse Merkle trees instead of Patricia trees. And the idea of sparse Merkle trees is that you can basically have it's basically like any normal Merkle tree, except that it's got an insanely large number of leaves. So you have 2 to the power of 256 leaves if you want to be able to represent every single SHA-256 hash as a key. And then if you want to look up that specific key, you basically hash the key and look up the corresponding index of that key in the tree. So like if the hash of the key is 1, then you look up the value in index 1, and that is basically the associated value with the key. So it's pretty simple, and it's much simpler than a Patricia tree, but it's as efficient, or almost as efficient as a Patricia tree, or as efficient as a standard Merkle tree, because the size of the Merkle proofs are still O log n, where n is the number of non-empty elements in the tree. So even though the tree has 2 to the power of 256 elements, you only care about the elements that you actually have any values in them. You don't care about the leaves that have 0 in them. So it's still efficient with regards to how many leaves in the tree have actual values in them that aren't 0. And so then we can imagine the blockchain as a state transition system. So if we have these state Merkle roots, these sparse Merkle tree Merkle roots that represent the state of the blockchain, and all of the UTXOs in the blockchain or the account, then we can basically imagine that each transaction applied sequentially modifies the Merkle root of the state in some way. So you can see there's many intermediate state roots between block X and block X plus 1. And so we can basically use these intermediate state roots to create an execution trace of the blockchain. And if we put these state roots, if we actually include these state roots in the blocks, then we can basically use this execution trace. And then the state root transition system takes in the state root, the transaction itself, and the witnesses, which I'll describe in a moment, and returns either the new state root or an error. And the witnesses of a transaction are basically the Merkle proofs of the part of the state root or the state tree that the transaction accesses. So you can basically prove to someone that some transaction modifies the state in some way without that person having the entire state of the blockchain, which is really useful. And this is a concept called the stateless client concept. There's been a bunch of work on that. So then the fraud proof itself, if you have the system, would be fairly simple. It would simply consist of the pre-state root, the post-state root, the transaction itself, and the witnesses for that transaction, and also all of the Merkle proofs for all of those things being included in the block header. And then once a full node can send the light client all of these things, light client can pass these things through the root transition function and see if the resulting state root actually matches the one in the blockchain, and if it doesn't, then the fraud proof would be valid. Or if the state root should be an error, then the fraud proof will be valid, and then the light client could reject the block. But the problem with this is that there's a problem called the data availability problem. The problem is, what if the miner doesn't actually release any of the transaction data? What if the miner simply publishes the block headers or directly passes the block headers to the light clients, and the light clients will accept these blocks because they're in the longest chain, for example, and then full nodes don't have access to the transaction data, and then as a result, the full nodes can't generate these fraud proofs because they don't have the data to generate the fraud proofs, because the miner has withheld the block data and only released the headers. So we basically need a way to guarantee that data is available. So Vitalik has proposed a neat way to do this that is based on erasure coding. The idea of erasure coding is that you can take some data that is X pieces long, and you can blow up that data to 2X pieces, such that if you lose any X pieces of that data, you can recover the entire data from any remaining X pieces. So effectively, this no longer becomes a 100% data availability problem. This is now a 50% data availability problem, because you only need 50% of the data to have access to the whole block, or to be able to recover the whole block. And so that means if a miner wants to hide even a single byte in this block, or not release a single byte in this block, they would have to not release half of the block. And what we can do with this is we can build random sampling scheme to get probabilistic guarantees that the data is available. So if we assume that the miner is actually trying to do this attack and has actually withheld 50% of the block, then the light client can randomly sample different parts of the block, and if it lands on a part of the block that is unavailable, that the miner hasn't released data for, then it won't receive a response for that part of the block. And if it doesn't receive a response for that part of the block, then it won't accept that block into its valid chain. So if you make one sample, there's a 50% chance that you land on a unavailable on an available block. After the second sample, there's a 25% chance of only landing on available blocks. Then there's a 12.5% chance, and so on and so forth. So then you get basically you get very high probability guarantees that you will actually land on an unavailable block if the miner has hidden 50% of the block. And with this scheme, the clients should gossip the samples that they have received to full nodes if they ask for them. So if a full node only has a part of the block, then a full node might ask the light client for the samples that it might not have, and this would basically allow the network to gossip these pieces until the network has half the block, and once they have half the block, they can recover the entire block and generate these fraud proofs. But also the thing to note with the scheme is that you need enough light clients to be making enough samples to actually reconstruct the entire data. And we'll do some analysis on that in a moment. But the problem with the scheme I've described so far with this type of erasure coding is that, well, what if the miner incorrectly generates the extended data? What if the miner incorrectly generates the erasure code? Like, they could just insert gibberish or nonsense into the extended data of the block. And so that's a problem, because then to prove to a light client that the extended data is incorrect, then you have to basically give them the entire original data of the block, and they have to recompute that extended data to see if it matches or not, or if it's correct or not. And the efficiency of that is O block size. So that's back to square one with Satoshi's roulette system. So to improve on this, we can use multidimensional erasure coding, so you basically arrange the data of the block into a square, and then you can individually extend the rows and columns of that square to make a bigger square. And then the size of if the miner incorrectly generates the extended data, then the size of the fraud proof would be limited to a single row or column. So then the efficiency of the system, or the fraud proof, or the size of the fraud proof would be square root block size, which is much better. And you can take this to higher dimensions. So in this scheme, it's 2-dimensional. You can go high. You can do higher dimensions, but there's trade-offs that I won't talk about here. So with this, the miner would have to hide around 25% of the entire square to make any part of it unavailable. And so if we look at the probability here, what is the probability of a client landing on at least one unavailable piece? The size is wrong, it should say unavailable piece. If the miner has hidden roughly 25% of the square. Because if the light client lands on an unavailable piece, then that means they have successfully noticed that the block is unavailable. And after 3 samples, it's pretty low, it's like 60%. After 15 samples, it's 99%, which is reasonably high. That might seem quite low, but actually, from an economic perspective, it's quite good, because that means on average, a miner would have to mine 100 blocks before they can trick an individual light client. You can also go high probability. So if you have 30 samples, you can get 99.99% probability. But I think 99 is good enough if you consider the economic implications of it. So as I mentioned, you need a minimum number of light clients to be making the sample requests. And also the other issue with this is that miners might decide to only release these pieces as clients ask for them. And if they do that, then they can fool the first number of clients that ask for these, because they can only release they might just release enough samples until they get to just 50%. And once they get to 50%, they can stop releasing samples. And so they've fooled everyone that already asked for the samples, but they can't fool everyone else. And here you can see the kind of numbers, and how many clients can be fooled depends on how many samples they make and how wide the square is. So with a 32 by 32 square, if you have 10 samples per client, then the number of clients that can be fooled is about 500. But ideally, we don't want any clients to be fooled, so there are ways to prevent that. Even though I don't think 500 is a bad number, because if you consider there's like 1 million people who have installed the Android Light Client or SPV wallet for Bitcoin, 500 is a very small proportion, but ideally still, we prefer that no one can get fooled, or everyone has the same high probability of not being fooled. And so if you consider that light clients can send the requests or the sampling requests anonymously, and then if they send them all at the same time or through a mixnet, so then you can assume that the order in which the network receives the sampling requests is uniformly random, so that effectively all of the requests are interleaved, then it wouldn't be possible for the network or a miner to selectively release samples to the light client, because they wouldn't be able to link different sample requests to the same light client. And so that would prevent the attack that I described in the previous slide. How much time do I have?
You've got another solid 10 minutes left.
Okay, so let's look at the security assumptions made by this system. So what additional security assumptions are necessary with different protocols so that the clients can be sure that they're only accepting valid blocks? And note that this is very different. What are valid blocks is very different to what blocks are in the longest chain. So full nodes, for example, they validate the blocks themselves. So they don't have to make any extra assumptions to be sure that the blocks are valid, except for things like making like the operating system is secure or stuff like that, or that their software isn't compromised. But if you use the full node as the baseline standard, then let's look at what additional assumptions light clients make. So in this table it says SPV clients, but I'm using the words SPV and light clients interchangeably. SPV basically stands for simple payment verification, which is the type of light client that's specific to Bitcoin. So light clients, standard light clients, they assume that the majority of the consensus set is honest when to ensure that all of the blocks they accept are valid and don't contain any invalid transactions. Now, if we add fraud proofs to the light client, we can eliminate the honest majority assumption and replace them with 3 much weaker assumptions, in my opinion. So the first assumption is that there's at least one honest full node in the connected network graph. And I think that's a very reasonable assumption, because if there isn't at least one honest full node in the entire network, then you're not going to be on the correct chain anyway, and you're potentially being eclipse attacked. Second assumption is that there's a maximum network delay to receive these fraud proofs. So if you're a light client and you see a new block header, then you should wait a certain amount of time to see if there's any fraud proofs for that block header. And so if you assume that, for example, you wait 5 minutes, so with Bitcoin's block interval it's 10 minutes, and so if we assume conservatively that you can receive a fraud proof in 5 minutes, or it takes 5 minutes to send a message to the whole network, I think that's a very reasonable assumption, because if you have a network delay higher than that, then I think you have bigger problems, including you're going to have a lot of forks on the network. But I think the strongest assumption here is the last one, which is that you need a minimum number of light clients, like a few hundred of them. So as long as you have a network that is popular enough, so that's such that there's always a few hundred light clients running, and if it's sharded, then there has to be a few hundred light clients per shard, then that scheme should work. And I think all of these 3 assumptions put together are significantly weaker assumptions than 51% of consensus is honest. And this is, so in Bitcoin, in standard blockchains, that's not really a big issue. Like you can probably assume that there's honest majority. Like for example, with Bitcoin, because you can validate the blockchain itself, and it's unlikely that there's going to be a 51% attack that is going to actually try to steal people's money, because there's so many people that are running full nodes that no one is going to be fooled. But with protocols that use sharding, then it's a really important problem, because it's not about the entire network. It's no longer about the entire network having a dishonest majority. It's about individual shards having dishonest majorities. So like if you randomly sample from a greater set of nodes to assign those to shards, and then you have like 100 shards, and oops, in one of the shards you randomly sampled a dishonest majority, then that dishonest shard, that corrupt shard can poison all of the other shards with its cross-shard transactions and poison invalid state into those 100 other shards. So in the context of sharding, and also in the context of very high on-chain throughput, for example, through bigger blocks, it's very important to try to eliminate this assumption for light clients. I'm not going to go too much into the performance, but it's in the paper. But overall, everything is reasonably efficient. In terms of space and bandwidth, everything is in a matter of kilobytes. The biggest overhead is in the fact that if you're a light client and you want to be sure that you have assurances that the data is available, then you basically have to download a Merkle route for each row and column in this square, and so that adds a lot of overhead to the block header. So with a block header that doesn't include that, it would be about 128 bytes. But with a block header that does include these Merkle routes, it will be about 2 kilobytes, which is I think it's a reasonable trade-off to have guarantees that their fraud proofs are available. Oops. Yeah, in terms of computation costs, everything is also quite reasonably efficient. Yeah. So I'll take any questions. Thank you.
Great, thank you, Mustafa. Are there any questions from the audience to start with? Well, I have an immediate question. I thought it was really interesting.
Yeah.
You mentioned a paper. Where should I go to read more about this?
Well, the slides were up. They were on slides. Let's see. Yeah, the link is here.
Great, thank you. Because that's really interesting. So do you foresee a future potentially where there will be lots of light clients using a security protocol like this and a smaller amount of full nodes?
Yeah, I mean, I think if you're going to do sharding, then I think it's absolutely necessary to have a system like that, because otherwise you're going to have a situation where corrupt shards can, as I said, poison the system. So this is something that Ethereum is actually thinking about as well. Yeah.
Great,
Patty? You mentioned that you need like 300 so light clients to run. Is that just for availability of the block? Like to force the miners to give it out?
Yeah, you're right. So basically, you need a sufficient number of light clients to sample enough of the block, such that the whole block can be recovered from the samples.
Okay, and then if a light client doesn't receive that, they just discard it and don't accept it immediately.
Yeah, if a light client doesn't receive a sample, then it assumes that the block is unavailable.
Thank you. Your mic's coming. I'll just hold on to this one.
Yeah, just a quick question. You had 3 repositories listed there for the code.
Yep.
What are these individual modules? Which one to look at for what functionality?
So there were three repositories. One of them was my implementation of a sparse Merkle tree. It's not a very efficient implementation, but it works and it has high test coverage. And there's also implementation of a Reed-Solomon of the Erasure coding data availability scheme. That's I think production ready, so you can import that if you wanted to. And finally, there's an actual prototype of the fraud-proof system. All of it is written in Go, by the way. Yeah.
Thanks.
Excellent. Well, if there are no further questions, then
there was one there, I think.
Oh, sorry. It's Sunday morning.
So in the context of when a light client receives an invalid or doesn't get the proofs, can they somehow make a request and slash the consensus mechanism if they do not provide data availability?
If the miner does, if the miner doesn't provide.
Yes, slash if data is not available.
So you can't actually do that because the problem with people have proposed using economic incentives or punishing people if they didn't publish blocks. But it's not really possible to do that, because if some data is unavailable, then that's a uniquely unattributable fault. It's like you don't know whose fault it is. Like it could be your fault because your network is poor, or it could be their fault because their network is poor. Yeah.
So I was just thinking, like, maybe can you have like a weird situation where the light clients reject it, but the other miners don't? Because maybe the miners don't share it. Like if I send it to another miner, maybe they don't share it on the network.
Well, I mean, in theory, miners should be running full nodes, or what miners are full nodes. So if a full node should download the entire block. So if a full node rejects the block because it's unavailable, then in theory, a light client should also reject that block. So I don't foresee a situation like that happening unless all the miners are actually running light clients.
Okay. They were at one point. They were SPV mining.
Yeah, I mean, then in that case, I think you'll still be fine even if the miners run light clients, because as I said, there's for each individual light client, there's very high probability of not being fooled. So like maybe you can trick 1% of the consensus. Yeah.
Great. Well, I think that is all we have time for to discuss this particular topic. Thank you,
Thanks.
Mustafa.